So let's wrap this section off of all this big gas and dust spread throughout the cosmos, and we'll tie them back into the stars and how they're starting to be birthed. And Orion Nebula, great example of this gas and dust floating around, and where you're going to find star forming regions. So on the right, we could have like our molecular cloud. And one way to think of a molecular cloud is that it's a star birthing factory, right? A lot of gas around here could start pulling together from just gravitational forces, and protostars can start to form in there. So as we look across the cosmos, where we see the density of stars or how they're dispersed actually gives us an idea of the age of the stars, right? The younger a star is, the more likely they're going to be clustered together because they formed inside the molecular cloud. So they're going to be close together when they went from protostar to star. Now, as the stars age, they still have some amount of motion in some random direction. So as the stars get older, the cluster of stars start to spread out. They start to disperse. So our young stars tend to be clustered together, whereas the older stars, because of just how long they've been around, allow them to disperse. These bullets is not a specific sequence of events. This is just bullet points of information. The exact sequence of going from molecular cloud to old stars is actually very complex and not fully understood. We don't have every piece of the picture of forming here to spread out. So think of these bullet points as just observations that we've made so far. Right. So last comment to make on this slide is that as the stars compress and spit out material, the massive stars, they tend to create a lot of ultraviolet radiation and high-speed gas. So the more massive a star is, the more likely it helps distribute the material of the molecular cloud, because it's releasing so much energy that basically is punching holes in the cloud. So now coming into a sequence of events. Here is an example of sequence of events of going from big cloud down to that star. And this is a bit of a recap from what we saw back in section 7, right? You have dense cores that form molecular cloud. So here's my molecular cloud. In this diagram, we're talking 5,000 astronomical units in size. Right. So this big, gigantic space. And if I was to zoom in on just one of these cores, so this material is just slightly denser regions inside the cloud. Zoom in on one of those denser regions, and that's where you're going to get your protostar. Remember, gravitational collapses, the protostar starts rotating faster and faster as gravity collapses in that pocket region. Right? So the protostar is all that hydrogen gas collapsing down, falling together. And eventually it's going to start producing a stellar wind. Basically, gravity's trying to squeeze things in, the rotation. What happens around the poles is that the star is literally ejecting material out. It's throwing material out into the cosmos. And we're going to see examples of this, these jet streams that these protostars form. And then eventually, that protostar will have condensed enough to collapse down into a single star. And it'll disperse all material around it. So here's an actual picture of a protostar and its corresponding jet stream. Notice this is over the space of a couple of years of the pole of this protostar constantly ejecting material out. Protostar formation will be upwards of thousands of years of it slowly collapsing down and ejecting gas in the cosmos. And here's another source of, say, hot gases in the intercloud space. This is material that didn't get absorbed by the star. It's not going to be part of its mass, but it got heated up and just flung out in the cosmos. So, like I said in the last section, we're going to start seeing these HR diagrams more and more because they're going to help us map the evolutionary paths. So, as a reminder, right, this red line is what we say is a main sequence stars. And our sun's somewhere around here in the G range of the spectrum on that main sequence. But the protostars, we still can plot them on the HR diagram. Remember, here's the luminosity versus the surface temperature. So you could have a star kind of like our sun, about 1 solar mass, and it'll be, at this point, still a protostar. And there's some interesting physics happening in its outer layers. Notice, the protostar, as it's getting older, is shrinking down. Right. What we're going to look at, I'm going to focus on this line here, right? The numbers on each line, these numbers here, they represent number of years. So if I start with a very massive star, that very massive star takes only about 10,000 years to go from denser region of the cloud to forming a star. Whereas the low mass stars, one that's like the 10th of our sun, they can take upwards to 1 million to 100 million years to finally collapse to a star. So the high mass stars will quickly, high mass protostars will quickly turn into a star. Low mass ones take a long time. But notice the track that they follow, where they take this long, this almost vertical track down. We call that the Hayashi track. So, points. The protostars, they are going to be more luminous than a star of similar size. The stars are going to be more luminous when they're way up here. The protostars are more luminous. And as that protostar shrinks down in size, right, it's going to start getting cooler. Its luminosity is going to decrease until eventually it hits the main sequence. It turns on fusion and starts to glow bright as a star. Right. So that's going to be the end of our discussion on the interstellar material out there. Just a quick reminder, we said space is a very low density but gigantic. There is billions and billions and billions of matter out there, and it's just dispersed in this huge, gigantic space. We've talked about how the gas and dust literally changes our perspective of the universe, sometimes blocking things, other times we can see through it using the right wavelengths. And the interstellar gas can have a wide range of temperatures, anywhere to being only 10 Kelvin. This is only 10 degrees Celsius above zero, upwards to 1 million or so Kelvin, because they're so energetic, rapidly flying around. So this gas has a wide range of kinetic energies and corresponding wavelengths of light it radiates in. And that final point is that you take a collapsing protostar to make a star, and as it collapses, it releases tons and tons of energy. So we'll call that into section 15, and I'll see you all next time.